Okay, welcome to this lecture today about data preprocessing. Now, data preprocessing is usually something which takes up more of your time as you initially wished for. It is a bit of a dry process because you don't get your fancy results that the machine learning models give you. It's more of like a step to actually make stuff happen. But it's quite an important step because often the things don't look as we anticipate them to look. So you might then later encounter some problems with your machine learning models, which you can then transfer back to the state of your data, that there are just some things which make it difficult for the model to actually learn what you wanted to learn. So some of these things which are just important to really get to know your data in the start, and also then to manipulate your data in a way such that you can extract these results you actually want to find out. This is what data preprocessing is about, and this is what we will discuss today a bit. Okay, so first let's go through some notations and assumptions we have for this lecture. So first of all, we assume that we have a data set with n observations. So here this number is n, and we have d features f1 until fd. And then our data is represented by a data matrix, which is n times d dimensional and contains only real values. So this is basically what's here inside this area. This is here our data matrix. And then we denote with mu fk the sample mean value of feature fk. So this is computed that we sum up all the values for the feature. So for example, the sample mean for f2 would be computed by summing up here all these values and then dividing them by n. And then we can compute here the vector of all mean values. So this is then the vector mu f, which gathers all the sample means for every feature. And then we denote here with sigma fk the variance. This is the sample variance of feature fk. You might have learned a different notation which uses here n-1 instead of n. So both computations of the variance are valid. It's just a matter of tradition in the field, what you use. So for example, in machine learning, we use here the sample variance. So this is called the sample variance, and if you divide by n-1, this is the population variance. If you compute the variance with numpy, then you will also get here this definition. But if you compute the variance with pandas, then it actually computes the population variance. So just be aware of this difference. Okay, so let's have a look at the basic data characteristics which are important. So you might have seen this in the news. It was in the time when we got our first invitations for the vaccine. And one of the stories was that a man got offered the vaccine due to his obesity. He became listed as obese because he was in the database registered as being 6.2 centimeter tall. This is just one of those things which you better just read out in your data before you actually do something with it. So data is just full of errors, and like the first step is that we actually have to create our data matrix. So that means that the data has to be represented by real values. And the process of making these features, which are for example here denoting categories, to convert them into numbers, this is called encoding. And for this we need to be aware of what the feature type is, because depending on the feature type, some encodings make more sense than others. And then of course we have also, next to the encoding, also some other issues. So for example, you might have here missing values. How to treat these missing values we will not cover in this lecture, but we will have a look at this later in the recommendation system lecture. And also it would be good to have a look at some statistics of your data to also see when there are some obvious outliers, like here for example when the height is denoted as 0.4 meters, or like the 6 centimeter tall dude. Like this should then all be identified first before you do something with your data. Now we have a look at the feature types, and the feature types are distinguished into qualitative and quantitative ones. So first of all, qualitative features, we have here either nominal data or ordinal data. Nominal data are usually categories which have no order, like for example, blue is not bigger or more than green, or so you cannot say anything like that. And ordinal data is similar, but there you have an order. But the thing is that the scale usually is quite subjective, so you don't really know what it means to consider, like the distance between the elements. So for example, you can think of a movie rating, like you can give 1 to 5 stars for a movie. But 1 star does not mean the same for every person. And also the differences are not necessarily always the same. So there might be a bigger gap between a 2-star movie and a 3-star movie than there is between a 3-star movie and a 4-star movie. Or another example are like clothing sizes like S, XL, M and so on. So here as well, like first of all, these sizes can depend on the clothing brand. And also the gap, between S and M is not really the same, like from M to L, for example. It's not like that you can really say that there is a well-defined distance which is between those values. But also you could say that, for example, your grade is an ordinal feature. For example, the difference between a 9.5 and a 10 is different than the difference between a 7.5 and an 8, right? But you see already that this might not always so clear, like what differences are well defined and what are not. But let's first have a look at what the alternative classification of features like this is. And the second category of features are the quantitative features, and there we have either discrete data or continuous data. And discrete data means that you have some kind of countable amount of values, and here the distances are meaningful. So for example, age would be a discrete feature. So there you already always know that, for example, the distance between being 22 and 23, like there's exactly 1 year in between, and this will always be the same. They have well-defined distances, same as like with number of children or number of yes votes, something like that. So like discrete data and ordinal data are in some sense quite similar, but just the difference is that for discrete data we have meaningful distances, and that is not so subjective. And then we have continuous data. I think it's straightforward, to get an idea about what that is. So these are things like measurements, where you also have meaningful distances, like everything which is like a meter, centimeter, degrees Celsius, income, like all these well-defined measure scales. Okay, so you might have seen in some of the examples that it's not always easy to identify the exact feature type. The thing is just that you should be aware of feature types and their differences, because not all encodings and statistics make sense for all types. Okay, so let's go a bit into what that means, and let's start here with the encodings. So the first encoding we discuss is ordinal encoding, and this is also usually used for ordinal data. And basically what it does is to map ordinal values to integers. So, for example, you have here these two features, like a picture, what the picture basically is showing, and then we have like some categories here, or we have like this other feature here, size, which is actually an ordinal feature because it has an order. these categories for the picture don't have an order, right? A dog is not smaller than a cat or whatever. Or a dog is not less than a cat, like you cannot make really here a meaningful order, but nevertheless we can also encode nominal data with this ordinal encoding. So for example, we have then here these two mappings. So this is here for the first feature, and then cat is 0, dog is 1, fish is 2, bird is 3. So what do we get here then? This is here dog, so dog is mapped to 1. So here should be a 1 and there is a 0. Okay, I will change that. And then we have here a cat, and the cat is mapped to a 0, and here I just did this all wrong. Okay. And so on. So fish is then mapped to 2. This is actually correct. And the same we do with the size. And here now you should really keep the order such that xs is smaller than s and 0 is also smaller than 1. So how do we do this then? S is then mapped to 1 here, right? And XL is mapped to 4 and S is again mapped to 1. Now this encoding suggests that the feature can be treated like a discrete feature when the feature is actually qualitative. So the numbers 0, 1, 2 and so on, they have well-defined distances. So 2 minus 1 is 1, but m minus s, is that 1? So is that s? It's like the difference between m and s. That doesn't really make sense. Do you get what I mean? Okay, so this is just like one of those things that actually this encoding suggests that the feature can be treated like a discrete feature, but actually these distances just don't make sense. And usually you would use this encoding for ordinal data, but it's also often applied for the class label. Okay, the second encoding is the one-hot encoding. So there we create for every category we have here in our nominal or ordinal data. So usually it's used for nominal data. For every category we create here now a new feature. So let's say, for example, the pictures we have in our data set either depict a cat or dog or fish or bird. Then this one feature of the picture is now transformed into 4 features, one for each category. And then we have here basically a Boolean indication of what category the picture is showing. So here we have the one at the feature dog, so that means that the picture is showing a dog, right? And here we have the one for the cat, and that means that the picture is showing a cat. Now what you see is that it increases the dimensionality of the feature space. But the advantage is that actually for nominal data this is quite suitable because it treats the categories as different as they are by creating a feature for every category, right? Okay, so now let's have a look at the statistics we can use depending on the feature types. So most of the statistics you know are eligible for quantitative data, but not always for qualitative data. So let's have a look at what we can reasonably do. For this we assume here now that we have a sequence of feature values x1 to xn, and we write here with these indices in parentheses the ordered sequence of the feature values. So that means that x in I parentheses is smaller than equal to xi plus 1 in parentheses. And then what kind of statistics can we have now? First of all, we can denote the mode. This is the most frequent value we have. For example, for our feature picture, this could be then the cat. If we have if cat is the most frequently occurring picture in our data set, and this we can do for ordinal and nominal data. Then we have the median, so this is basically the value in the middle of our ordered sequence. The middle is not always, like an element, right? If it's only an element if n is odd. Like then we have really one element which is straight in the middle, and this is then the element with the index n plus 1 over 2. And otherwise we just average the two values we have, which are closest to the middle. And for nominal data, this doesn't make sense because nominal data doesn't have an order, right? But for ordinal data, this is eligible. And then we have our beloved mean value. Sample mean is here denoted. And this doesn't make sense for nominal data because, what is the mean between cat, bird, and fish? You cannot really compute in it. It doesn't really have any meaning, even if you use your encoding and then, I don't know, you get a number of 3.5 as the mean, and 3 is a bird. It doesn't tell you anything, right? And if you're really strict about it, then it's also not eligible for ordinal data. And the reason for this is just properties of the ordinal data, that it's so subjective, like if you have a subjective scale, like for example movie ratings or so, then computing the mean is not very meaningful. Also like the mean value of clothing sizes, like if you get then it's 3.7 or so, and 3 is, the value of M, then you can say like, okay, maybe it's something between M and L, but because the distances are not so well defined, the 0.7 distance from 3 doesn't really have any meaning. And when we don't have the mean for these qualitative feature types, then we can also not reasonably compute the variance, right? Because the variance requires the mean. Okay, this just to have it in mind. And in addition to looking at the statistics, it's also always good to plot your data, like to have a visual representation, because then you can really see things. And for this we have a look at the iris dataset. So this is a really often used dataset in machine learning and data mining. It's a classification dataset of iris plants, and the task is to differentiate the classes of versicolor, setosa, and virginica based on measurements of the sepal length, the sepal width, the petal length, and the petal width. Okay, so this is our data set. You see here we have 4 features. We cannot plot the data in the feature space because we cannot plot in 4D. But what we can do is, for example, a scatter plot. So that means we plot all pairs of features we have against each other. So for example, here we combine sepal length with sepal width, and then we combine sepal length with petal length, sepal length with petal width, and so on, right? Until we have all kinds of combinations. So these create then these 2-dimensional views, and the color we have here for our data points corresponds to the class. And then we can see already that in some of these views, the classes seem to be more easily differentiable than other views. So for example, this view is actually quite good, right? Because here you have probably a bit of overlap over here, but by and large, these classes are quite well separated. And a thing you can also see is that this blue class here is in all views usually better separable than, for example, the green and the red class. So you can take already from this that it might be more difficult to separate red and green than blue, But we also see that most of these observations we have here actually cluster quite well. So it's not like we have here, for example, some outliers, so that one of the data points is all of a sudden here or so, or here. So everything looks already quite neat. And then you can also do a box plot, which is usually a really nice visualization of the statistics of your data. So here we have the features, and then we have here the median, which is indicated by this middle line, and then we have the quantiles, the 75% quantile and the 25% quantile indicated by this box here. So the 25% quantile indicates the value here, which is, for example, 1.5 or so. So that means that 25% of my observations actually have a value smaller than or equal to 1.5, and the median is actually the 50% quantile. So that means that 50% of the data lie below the value 4.1 or what it is. And then we have here also the minimum and the maximum, but this is not usually not the exact maximum and minimum you observe in your data, but it's also bounded by a rule of thumb which uses here this interquantile range. So this is here the length of this box here. You see here this, for example, for this feature supple width. So here we have some outliers indicated. So data entries which are actually outside of the maximum and minimum here. So this is a nice indication of possible outliers and stuff, but I wouldn't interpret too much into it. So these outliers or these indicated outliers are still quite close here to this value. I don't think that you could actually say that they are real outliers. So if you have no data which is over here, then maybe this is a good indication to look at what's happening there, right? But this is just a good visual depiction of what could be some characteristics of your data. Okay, thank you. This was it for the first part of our lecture. So we have seen a bit about the data characteristics and what we can do to get to know our data. And now in the second part, we will then discuss how we maybe can transform our data into a suitable format.